My name is Martin Grabmüller and Dirk is hiding somewhere. It's joint work and we have written a library for runtime code generation in Haskell. There's a little problem because making a demo of a library is not easy. So I decided to make a demo of actually two applications. One's large and designed to impress you, and one is small, designed to be understandable.
Excuse me, can you use the microphone?
Oh, sorry. That's why nobody was laughing. Okay. Better?
Yep.
Okay. Okay. Harpy, as the library is called, is a Haskell library for runtime code generation. It's better here. And it generates x86 machine code, actual machine code as executed by Intel processors, or AMD or whatever. And it provides management for labels, source code labels, code buffers, etc., etc., so that it is quite easy to write machine-level programs in Haskell. You might wonder why we do this. Maybe you will see. Okay. We make use of several of Haskell's advanced language features to provide a monadic domain-specific language for assembler programming, so that the notational overhead is minimal when writing assembler functions. And we use, for example, template Haskell to reduce the amount of boilerplate code to write. Okay, first part of the demo. I've written a small sample program which is a small interpreter. Called the harpy interpreter. And I will go through a few of the commands. One moment. Okay, we have a help screen here. So the idea is that you can enter arithmetic expressions and get them evaluated. You can set variables. You can reference variables, and well, a few other commands we'll come to later to. And it will do the obvious thing. Well, mostly obvious. You can tell that it's doing integer arithmetic, and actually it's doing unsigned integer arithmetic. It's just to make the program, which I will show later, more easy to understand. Okay. So I said you can set variables. Let's do that. Stick to the example. So nothing happens, but when you now look at A, you see that there's one stored in it, and you can use the variables in expressions as well. That's easy. You can do it in about 15 minutes in Haskell, write a small interpreter. Let's see where it differs from that. Okay, if I've counted right, this is about the 6th implementation of these expressions today. We have statements, assignment statements and print statements, and assignment variables are simply represented by characters, and those expressions are the usual arithmetic expressions, literals, and variables. So now the idea is not to write a simple, straightforward interpreter in Haskell, but we would like to do something more difficult. We want to write actual machine code on the run, on the fly, and call this machine code to evaluate the expressions. I've picked out one small function from this expression evaluator to give you a feeling of how those functions are written. This is the compiler. It takes an expression from the data type we've just seen. And the return is a monad, the code in monad, which is part of the library. And it has some additional type parameters. This pointer to word 32 values is actually the storage space for variables. And it's an array of 32-bit values, and we reference it by a pointer, so that later in the assembler code we can directly reference the right component of this array. Additionally, you can pass through the state S. In this example, we don't need it, but when you write a real compiler, you will probably need to thread some state through the compilation process. So the first part, the pointer, is kind of an environment, and the second is a state. And the last, the unit is the result, so every code generator can, in addition to generating code, return some result. Okay, let's compile some code for literals. This is quite easy. We have a convention that the result of an expression evaluation appears in a specific machine register, EAX, and the library exports a function called move, which generates the code. So we simply write move EAXI. That's all. Let's do a variable. It's a bit more difficult. We fetch the environment from, the environment is such an array, and we have a helper function which calculates the address of this particular variable in the array. So there will only appear constants in the machine code. And what we do here is move EAX and an address. So what you can see here is that move is an overloaded function, and we have made use of multi-parameter type classes to provide all the addressing modes that which are provided by this processor. Let's do some arithmetic. Not so difficult. It's a simple scheme. We compile the second sub-expression, then we put it onto the runtime stack, compile the second, and perform an addition of the AX and the current top of stack. Yeah. This is another addressing mode, which means indirect through register ESP. And then the last one is we clean up the stack so that it doesn't grow without limit. And the other ones are quite similar. They don't add, instead of add itself, just add a little bit additionally. Okay, let's look at the result. So I will put predefined value into A, so start safe. And now I switch on the verbose mode. But remember the interpreter is only a prototype, it's just a tool to present the ideas here. It's not a real program, so don't try to make use of it. Okay, now I have switched on disassembly. So that means that for every expression I enter, it will generate the code, execute it, and show me a disassembly. Okay, let's do something simple. One. Can you see that in the back? Well, this is the idea here. The two instructions at the top and the three at the bottom simply set up a stack frame and clean it up so that calling into this machine level function will work and not destroy all your Haskell internal state. And the only useful thing is that there's loaded the constant 1 into register EAX, and this is the value actually returned. For variable, we simply move the value from a constant address. The address of this variable was calculated at compile time and will remain just for the execution of this one statement. So in this example, for every evaluation, a new set of variables is allocated, etc. Okay, then we can do the example previously. 4 times complicated. And you see, this is the actual machine code generated by this demo program.
So, good question. So every time you type an expression, you're generating this code, you're putting it into memory, you're jumping to it, you're getting the result back,
Yes.
and then you're printing it.
Yes.
Sorry, behind you.
Okay, that's what I meant by impressing. Now the smaller but simpler program. This is a complete program. You can take this code, compile it, run it, and have a little bit of runtime code generation, just-in-time compilation for Haskell. I'll just explain a few things. You have to import the library, of course. Come to this part over there later. Here. Here is the function which generates code. So every monadic action in this monad is a code generator, and you can combine them, you can sequence them, you can use all tools for monadic programming you want. For example, this one. You can generate code and then run it. And running the code is down there, which calls a function called call as word32. This jumps into the generated code and returns a result of type word32. And because there are a lot of data types, and we can predefine such calling function for each use to be imagined, we have made use of template Haskell to generate these functions automatically. And this is the part over there. This call decal function takes the name of the function and the type, here quoted in template Haskell syntax, and then the function walks over the type and generates the correct code for calling such a function. So you can even generate functions which take parameters. Yeah. And yeah, we have the code generator, how to run it, and then we need an additional function to actually kick off the computation, and that's the run token function, which takes such a monadic action in environment state, evaluates it, and the result is shown. Okay. Questions? Yeah?
What happens if we divide by 0 or create some exception in your assembly code?
Everything breaks.
Okay.
So I was expecting that the run code gen thing would be what spat it into memory and jumped to it. But now you say this little run guy does that. So which code does he run? He might sort of all. He might be
The thing is, this is kind of the top level. This is the top level run generation. You can have several of those.
Yeah. So can you give an example when that's useful?
Well, we're working on, I'm working on runtime code generation for functional programming, where you incrementally generate code. So the example would be that the whole program is embedded in this run code again, and then does some code generation, some execution, some code generation, execution, etc. So it could work. What you can do too is you can call from this code into Haskell, and you can call back. So that's another very useful feature that for debugging, for example, you can call actual Haskell code, passing all those types which are marshalable through the FFI.
The Intel assembly language is rather heavily overloaded compared with the binary encoding of its instruction set, and I wondered if you've made any use of type classes to resolve that overloading at compile time, or if it's all done dynamically by the Intel.
This is done by multi-parameter type classes. So we have about 400 type classes or something, and 1,000 or so methods for implementing about 100 or so machine instruction with up to 5 addressing modes. Move is a nice example. For move there are 7 or 8 or 20 combinations, I think.